Sir Isaac Newton, a comprehensive and detailed study of his life and work. Isaac Newton, 1643 to 1727, was an English polymath whose contributions to science, mathematics, and philosophy revolutionized the intellectual world. His profound influence remains evident across multiple fields, shaping not only physics but also mathematics, astronomy, and even philosophy. Here, we'll delve deeper into his life, work, and the far-reaching impact of his discoveries. Early life and education. Isaac Newton was born on January 4, 1643, in Woolsthorpe, Lincolnshire, England, into a family of farmers. His father, also named Isaac Newton, died 3 months before he was born. Left without a father, Newton's early years were spent in relative isolation, raised by his maternal grandmother after his mother remarried. Newton had a solitary childhood, often showing little interest in the family farm, where his mother had hoped he would become a farmer. He attended the King's School in Grantham and later enrolled at the University of Cambridge in 1661 at the age of 18. There, he studied at Trinity College, Cambridge, initially pursuing a degree in law. However, his interests quickly shifted to natural philosophy, a term used for what we now call science. Under the mentorship of mathematician and astronomer Isaac Barrow, Newton became deeply engrossed in mathematical studies. Newton's university years coincided with the period of the scientific revolution, where groundbreaking ideas were being introduced by figures such as Galileo Galilei, Johannes Kepler, and René Descartes. Influenced by their work, Newton began his own experiments and observations, which would eventually lead to groundbreaking discoveries. Development of key concepts. Newton's contributions to science are so vast and interconnected that it's often difficult to separate one discovery from another. Below is an in-depth look at the areas in which Newton made the most significant strides. 1. Laws of motion. Newton's 3 laws of motion form the foundation of classical mechanics. These laws provide a framework for understanding the movement of objects, both on Earth and in space. These principles were revolutionary at the time because they replaced Aristotelian ideas, which had dominated Western thinking for centuries. 1. First law, law of inertia. This states that a body will stay at rest or continue moving at a constant velocity in a straight line unless acted upon by an external force. 1. This concept challenged earlier notions, such as Aristotle's, which suggested that objects need a force to keep moving. 2. Second law, F equals ma. This fundamental principle expresses that the force acting on an object is equal to its mass times its acceleration. 2. This is a key relationship in classical mechanics and helps explain how forces affect the motion of objects. 3. Third law. This states that for every action, there is an equal and opposite reaction. 3. It explains the interactions between objects, such as how a rocket's engines push exhaust gases downward, which in turn propels the rocket upward. These laws not only transformed the study of motion on Earth but also provided a mathematical framework for analyzing the motion of celestial bodies. 2. Universal law of gravitation. Newton's law of universal gravitation is arguably his most famous discovery. This law posits that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Mathematically, it's expressed as F equals G dot operator M1 dot operator M2 R2 F equals frac G C dot M underscore 1 C dot M underscore 2 R squared F equals R2 G dot operator M1 M2 where 1. FFF is the force of attraction between two masses. 2. GGG is the gravitational constant. 3. M1 meter underscore 1 meter 1 and M2 meters underscore 2 meters 2 are the two masses. 4. RRR is the distance between the centers of the masses. The implications of this law were vast. It not only explained why objects fall to the ground on Earth but also provided a mathematical framework for understanding the movements of planets, moons, and other celestial bodies. Newton used this law to confirm that the elliptical orbits of planets, as described by Kepler, were due to gravitational forces acting between the Sun and the planets. 3. Calculus. Newton developed calculus, which he referred to as the method of fluxions, around the same time as German mathematician Gottfried Wilhelm Leibniz. Although both Newton and Leibniz independently developed calculus, the dispute over who was the first to invent it led to a bitter conflict between their followers. Nevertheless, calculus became one of the most important tools in mathematics. Calculus is the branch of mathematics that deals with rates of change and the summation of infinitely small quantities. It has two primary branches. 1. Differential calculus, which deals with rates of change and slopes of curves. 2. Integral calculus, which deals with the summation of infinitely small quantities, such as areas under curves. Newton used calculus to explain the motion of objects under forces and the behavior of fluids, and later used it to solve problems in astronomy, such as calculating the orbits of planets. 4. Optics and the nature of light. Newton's experiments with light and color were foundational to the study of optics. In 1666, while still a student at Cambridge, Newton experimented with a prism and discovered that white light is not pure but is a mixture of different colors. He showed that when light passed through a prism, it separated into a spectrum of colors, which could be recombined to form white light again. In his 1704 work Optics, Newton explored the properties of light in more detail, proposing that light is composed of particles, corpuscles, which was in contrast to the wave theory of light that was later developed. Newton's particle theory of light was influential, though it was ultimately overshadowed by the wave theory in the 19th century, and his findings on color and optics laid the foundation for the study of light's behavior. Newton's work in optics also led him to design the first practical reflecting telescope, which solved the problem of chromatic aberration found in refracting telescopes. His telescope used a concave mirror to gather and focus light, making it much more efficient and allowing for clearer observations of celestial objects. 5. The Principia. Newton's most famous and influential work is Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, first published in 1687. The Principia is a comprehensive work that laid the groundwork for classical mechanics. In it, Newton described his laws of motion, the law of universal gravitation, and their applications to planetary motion. The Principia is one of the most important scientific works ever written, as it not only explains the motion of celestial bodies in mathematical terms but also unifies the study of motion on Earth with the motions of planets and stars in space. Newton's explanation of the elliptical orbits of planets and the behavior of tides was a major advancement in both astronomy and physics. Personal life and beliefs. Newton was known for his intense focus on work, often becoming absorbed in his studies for long periods of time. He had few close relationships and was known for being somewhat reclusive. He never married, and his personal life was often overshadowed by his intellectual pursuits. Newton's temperament was reportedly complex, as he could be both intense and deeply insecure, particularly regarding his ideas and his intellectual battles with others. Though his work in science was groundbreaking, Newton was also interested in philosophy and religion. He spent many years studying alchemy, the Bible, and theology, although he kept much of his religious and esoteric research private. His religious beliefs were unconventional for his time, and he was particularly concerned with understanding the nature of God and the universe. Newton's alchemical work, although largely dismissed today, was also a part of his quest to understand the physical world at a deeper level. Later life and legacy. Newton spent the latter part of his life in public service. In 1696, he became Warden of the Royal Mint, where he oversaw the recoinage of the nation's currency, combating counterfeiting. He was later appointed Master of the Royal Mint, a position he held until his death. Newton's influence in science was unmatched. His work not only provided the foundational principles of mechanics and astronomy but also inspired future generations of scientists, including Albert Einstein, who later acknowledged Newton's work as the foundation of modern physics. Einstein's theory of relativity, for example, expanded upon Newtonian mechanics by incorporating a more accurate description of gravity in extreme conditions, but Newton's laws remain a valid approximation for everyday phenomena. Newton died on March 31, 1727, at the age of 84, and was buried in Westminster Abbey, a testament to the immense respect he garnered in his lifetime. His tomb bears an inscription that reads, "Here lies Sir Isaac Newton, who by his profound thoughts and keen reasonings, discovered the laws that govern the movement of the heavens and the earth, which have long been the delight of all mankind." Newton's lasting impact. Newton's discoveries laid the foundation for much of modern science. His laws of motion and gravitation became the pillars of classical mechanics, a discipline that held sway until the early 20th century. His work in mathematics, particularly calculus, has shaped not only physics but engineering, economics, biology, and many other fields. In summary, Isaac Newton's genius lay not only in his discoveries but also in his ability to unite disparate fields of knowledge, mathematics, physics, and astronomy, into a unified framework. His work continues to influence modern science, and his legacy is one of unparalleled intellectual achievement.